Pioneered and developed at the Center for Space Nuclear Research, radioisotope and nuclear fuel encapsulation within tungsten ceramic metallic matrices, known as Cermets, by the spark plasma sintering process, or SPS, offers many advantages in operational safety and security over traditional encapsulation technologies. The process begins with the assembly of an electrically conductive die, the geometry of which results in the net shape of the finished Cermet product. Graphite is most commonly used for die fabrication. The dies are assembled within a controlled inert environment so as to prevent oxidation of the tungsten powdered feedstock materials. The Cermets are composed of a mixture of tungsten powder with ceramic compounds of nuclear materials, the ratio of which drives the operational performance of the product. In the example provided here, cerium dioxide is used as a surrogate to simulate nuclear materials such as uranium dioxide. Once mixed, the powder is poured into a die lined with a lubricating material, in this case graph oil. The die is closed at both ends via the installation of punches. These punches are used to provide good electrical contact between the SPS furnace and the powdered materials, and to transfer mechanical pressure applied via hydraulic rams within the furnace. Once assembled, the die is sealed and removed from the inert environment glove box for installation within the SPS furnace. Once the transfer is complete, the die is placed onto the lower of two hydraulic rams within the vacuum chamber of the SPS furnace. An optical pyrometer is used to provide feedback to the temperature control system of the furnace. This must be aligned to the die prior to the closure of the vacuum chamber. Air is removed from the chamber prior to the execution of the process to prevent oxidation of the die and interior of the furnace while at high temperatures. An automated control system is used to apply a prescribed amount of pressure upon the die, while a strict temperature profile is followed. Consolidation of the powdered materials to approximately 95% of their theoretical density is possible at temperatures that are significantly lower than their melting points. Here, a sample is sintered at only 1400 degrees C. Once the process is complete, the die is cooled via a water coolant system so that it may be removed from the furnace by hand and returned to the inert environment glove box. Upon returning to the glove box, the product Cermet may be removed for inspection. If required, the Cermets may be transferred to a secondary die where an outer encapsulation jacket may be applied, or Cermets bonded to create elements of a desired length. This can be achieved by repeating a similar process using the SPS furnace. Little to no post-sinter processing of the product Cermets is required, and via careful die design, unique features, such as the flow channels shown in this example, may be produced during the process.